right, so this is, well, I guess yet another video. It's for section 8.6. It's just going to be one example, so sort of a quick video, a likelihood ratio test example, all right, with two simple hypotheses. Okay, so why don't you pause, copy third bit of algebra, and then press play. All right, so in this example, we've got a random sample of n from a Bernoulli distribution with probability p. So think of that as n trials. Probability of success is p for each trial. They're independent. X1 will equal 1 if it's a success, and it'll equal 0 if it's a failure, okay? Our null hypothesis is that the probability of success is 0.4, and the alternate hypothesis is the probability of success is 0.5, right? And we like to test that via the likelihood ratio test, okay? So what we're going to use as a tool or to get towards our t is the sum of the xi's, so the number of successful trials, which we know follows a binomial distribution with n trials probability of success p. The sum of Bernoulli's is a binomial, right? So let's set up t. T is the likelihood of the data if the probability is 0.4 divided by the likelihood of the data if the probability is 0.5. Now the data is the sum of the xi's. So the probability of the sum of the xi's equaling x with 0.4, according to the PMF of a binomial distribution, is n trials, choose x of them to be successful. X of them have success, so 0.4 to the x, and the rest of them have failure, so 0.6 to the n minus x. And in the denominator, it's the same story with the probability being 0.5 and 0.5 instead of 0.4 and 0.6. Okay, now we get into some algebra. The n choose x's cancel. 0.4 to the x over 0.5 to the x is 4/5 to the x. We mush them together because they have the same exponent. And then this guy, I split it, so it's an nth power and a negative x power. So it's 0.6 over 0.5, both to the n, so that's 6/5 to the n. And then it's 0.6 over 0.5 to the negative x, so it's 6/5 to the negative x. Okay. All right, next line down, 6 over 5 is 1.2. So 6/5 to the n is 1.2 to the n. There's my 4/5 to the x. And to get rid of the negative exponent, I can just do 1 over 6/5. So that'd be 5/6 to the positive x, right? Great. Well, since they both have the positive x power, I can now multiply the insides together. So the 5's cancel, and I'm left with 4/6 to the x, and 4/6 is the same as 2/3. Okay. So I've calculated my t statistic, I've simplified it, and the likelihood ratio test says that I should reject the null hypothesis if this ratio, which I've calculated, is small enough, is less than some threshold c, which we haven't figured out yet, but less than c. So I'm going to try and take this inequality and solve it for x, because I'm trying to get a critical region so I know when to reject the null hypothesis. So I'd like to get the critical region in terms of x, the number of successful trials. Okay, well, to get at x, I need to get at that power. So the natural thing to do is to take the natural log of both sides. Since the natural log is an increasing function, it preserves the inequality. If this quantity is less than this quantity, the natural log of the first quantity is still less than the natural log of the second quantity because the natural log is an increasing function. I guess it's actually good. Okay, well, I can split multiplication there with addition. The exponents get dragged down. I can subtract over the n times the ln of 1.2. And then I can divide over the ln of 2/3. But when I do, remember, ln of 2/3, you can check in your calculator, it's a negative value, so the inequality flips. So it turns out that we reject h0 when x is greater than this monstrosity, which I'll just call some constant c2, okay? All right, and then we're going to grab this result and take it over to the next panel, which is the last panel. All right, so pause, copy, play. All right, so we're going to reject the null hypothesis when x is greater than c2. That means our critical region is when x is greater than c2. So it's all possible n trials, and the number of successes is greater than c2. Okay, so let's actually provide some information and come up with this critical region. Let's suppose that we've run 10 trials of whatever this experiment is, and we desire a significance level of 0.05. So that means I'm okay rejecting the null hypothesis incorrectly. So rejecting the null hypothesis when it was actually true up to 5% of the time. I'm okay with that, all right? So I want a critical region that provides no more than 5% of the time an incorrect rejection of H naught, the null hypothesis. All right, well, 0.05 is by definition the probability that I reject H naught when H naught was correct. I'm going to reject H naught when X is greater than C2. That's what we figured out from the likelihood ratio test. And H naught being correct means that the probability of success in each trial is 0.4, okay? So in other words, 0.05 is the probability that X is greater than C2, where X is binomially distributed with 10 trials of probability of success 0.4, okay? All right, well, that's a pretty darn definite distribution, because these were simple hypotheses. If I tell you P, if we knew N, that uniquely determines the distribution. So let's figure this out. And let's just guess and check. Let's suppose I thought C2 is equal to 7. And X is binomial 10, 0.4. The probability that X is greater than 7 is, it's basically a probability of having 8 successes, 9 successes, or 10 successes. So R can do that, do the sum of the binomial distribution from 8 to 10 successes out of 10 trials with probability of success in each trial 0.4, and it gave me 0.012. That's nowhere close to 0.05. So I'm thinking, okay, well, I guessed too high. So let's now guess that C2 is actually 6. Run through the same computation. Okay, and now I get 0.055, which is larger than my desired alpha of 0.05. But because binomial is discrete, these are my only two choices if I want to be around 0.05, okay? So you can either say, hey, I'm going to either accept an alpha of 0.055, or I'm going to accept an alpha less than 0.055. So I decided, you know what, we're going to go with the less than. So we're going to set C2 to be 7, which provides an alpha of 0.012. Thus, the summary here is the critical region for rejecting the null hypothesis, so rejecting P to be 0.4 and accepting that's 0.05, 0.5, is this region where the number of successes is strictly greater than 7, okay? So if I see strictly greater than 7, if I see 8, 9, or 10 successes, I reject that the probability of success is 0.4 and I accept that it's 0.5. If I see 6 successes or fewer, I accept that the probability of success was 0.4.